Hi there. I just posted this to my data blog. This one's called "Looks Perfectly Flat and Level to Me." This is another lake test. You may have seen the video that I posted around 8 days ago of the results that I collected and analyzed here on Union Lake in Millville. That video is called Flat Level Lake Measurements. Using the lake as a level to set points that would be a level with each other, using the water surface to do that. And this turned out real well. Not very dramatic, but it showed me, this was worth pursuing. So I went ahead and close that. I went ahead to this location along the Cooper River, which this area is called Cooper River Lake because it's above a dam and it is not tidal anymore. The water does rise and fall a little bit here and there, but basically it's just a level lake. And as you look at what I'm going to post and show you here, you'll find out that that's what I found out. It's actually level. And what was nice is that I had a much longer line. It's over a mile. It's about a mile, 1.38 miles. It's 7,311 feet, this line. And I set points at either end, at the eastern side and at the western side. And I'm going to show you that. What I did is I just set a spike, a nice long spike, 60 millimeters above the water. Then I set another one back from that about 3 feet, just using this little 3-foot carpenter's level, and made sure that it was level. And you can see that here. So this is the point that I'm referencing to the water, 60 millimeters, and this is the point that I'll be occupying, and they are level with each other. So, I mean, this makes sense, certainly, right? So I did that on both sides, and I did that very quickly. I set one and drove. I had the other one set within 5-10 minutes, really. And then, of course, I'm showing you how I set up my targets, measuring to the notch here. It's a very precise measurement. I called these points Cooper 2 and Cooper 1 with the date. Here's a measurement from the notch to the center of the target, and when you add these together, you end up with a true height of 1.613 meters. So there's the target at point 2, aimed and looking back at point 1. All right, so now I'm going to go over here to point 1 and assure that the telescope is set at the same height, and make sure that the instrument is very precisely leveled before making the observations. And then here I snap a shot through the telescope with the telescope set to be horizontal. And there's the target. It is definitely below the horizontal crosshair, yet they are at the same elevation. And this is what I expected to see. I'm reporting it to you here. I'm not not making this up. This is really what you will see. And I really do encourage people to go and see this for themselves. This is not that hard to do. You've probably seen some videos of people doing lake tests along, laser tests, across gigantic lakes with a lot of waves and this and that. You can do the same thing on a 1 to 2 mile long lake that's nice and calm. You don't have to go 10 and 20 miles. I mean, you'll start to see the results of this in short distances. I did see the same thing on the shorter distance in my first lake test over on Union Lake. It's just a smaller amount, that's all. Anyway, continuing on, I have a zoomed in picture for you to see. And I've moved my crosshair over a little bit so you can see the target. There's the horizontal crosshair, and it's set here on the point 1 side, on the eastern side. It is set at the same height as that target is set above the spike over there. That's just how it is. You can't get away from it. There it is. So moving on. And by the way, I'm going to go ahead and also indicate that I've measured 6 sets of zenith angles from 1 to 2, and here are the results with the precisions out of that set of measurements. So then I do the same thing. Now I'm going to move my theodolite across the water, and I'm going to leave the target here at point 1, and I'll move the theodolite over to point 2. And again, going for the same height to do the same thing again, so that we get near real-time reciprocal zenith angles. That's what this is called. And there we go. So I'm just recording all this for you to see. And again, now I'm set up at point 2, looking back at 1. Once again, I've set the telescope to be horizontal, and zooming in, you can see that the crosshair is over top of the target. There you go. So, from one end of the line to the other, and from the other side of the line back, we're seeing the same thing. Draw your own conclusions. All right. So, and again, 6 sets of zenith angles. Here we go. There's the result. All of this is tabulated down at the bottom. I will leave a link to this blog in the video description box. Okay, then I thought, well, I'm going to just take a break now. You noticed in the first test I did on Union Lake, I had the GNSS receivers running simultaneously while I measured the zenith angles. That was a good method. This time I wanted to do it and have them be separated because I wanted you to see that these GNSS observations have really nothing to do with the zenith angle results that I'm getting. So I actually did them separate. Okay, so here I took a break from the zenith angles and I set up two GNSS receivers to log multi-constellation, multi-frequency. And what we're talking about here is it is not just GPS, it's GLONASS, which is the Russian system, and GPS combined. There might even be some Galileo in there, but there's still not very many of those satellites up there yet. But anyway, I've got 45 minutes of simultaneous recording of data at both ends of the line, which can then be post-processed to solve for the vector between the 2 points. So once that was done, I decided to then set up the target and the theodolite again for a completely separate, independent set of observations. So here we are, putting the target precisely leveled over 0.2 again, and measuring the height. This time it's an absolutely different height. Still, above the spike, which is 60 millimeters above the water. And here we have the target now set at a height of 1588 meters above the spike, aiming back at 0.1. Now over here, we see that it's quite easy to make a mistake, even when you're taking great care. So I'm reporting it. I'll let you see it, and I will document what happened. Up here you can see that I measured 1.43. What did I do here? I set this thing at 1.34. And, I'm flying, I'm doing this all by myself. So I don't have a note keeper. I don't have an observer. Usually a survey party has several people involved. I'm doing this all by myself. And bam, here's a mistake, 1340. And I didn't catch it. And I literally measured a whole set of zenith angles at the incorrect height. All right. Now, when I took this picture, I should have known immediately, but, I'm flying here trying to get this done, and, oh well. So, yeah, I recorded, and I report them here. Hey, for what it's worth, here's these 6 zenith angles measured at this different height, which is useful. You could look at the difference, compute the difference in the height, and do some analysis of that. I didn't bother to do that. I'm just reporting it here. Maybe somebody else will look at it. But here it is. So I'm saying here, as discouraging as it was, and let me tell you, when I found that this happened, I just looked at the water and thought, I wonder if I have enough information to just leave right now, because it was a bummer, and but I persevered. I said, no, you got to keep going. You need this second set. So I broke it all down, reset it up, and got it back at 1430. And there we go. So this is, what you're going to see next are the pictures where the instrument is set at the correct height. And again, I set the telescope to be 90 degrees, zenith angle of 90 degrees, which means that this horizontal crosshair is the horizontal plane extended from where I'm observing from. That's exactly what it is. And so just as before, we are seeing that the horizontal crosshair is over the target. Okay? And there's a close-up of that for you to see. And then I measured my 6 sets of zenith angles again, report them here. Once again, now I'm going to prepare that the target is going to be set at the same height, and I'm going to move the theodolite across the water to 0.2. So here's the target all ready to go, aiming at 0.2, and it's sitting at 0.1 at this new height of 1.588. above the spike. Spike's 60 millimeters above the water. Okay, so here's the telescope now set up at 0.2, same height. And looking back, we have a picture zoomed in showing you that the crosshair is once again above the target over on 0.1. All right, that's all stated here. Then I actually record zenith angles directly to the target. 6 sets. There's the standard deviation. There's the standard error of the mean. Okay, after the second set of zenith angles were measured, I closed out the day by just setting up the GNSS receivers once again on both sides of the lake and recorded 55 minutes of simultaneous data. It was about 20 minutes till 1 o'clock, and it went for 44 minutes. And then, of course, I did the next set of zenith angles, and then after that, at nearly 4 o'clock, I started it up again on both sides and recorded 55 minutes of data. And so here you are. It's from 1 to 2 both times. I report the RMS out of the software, the number of satellites that were tracked, the dx, dy, dz, and the vector length. We also have the ellipsoid distance and the delta ellipsoid height and the azimuth. Okay. Now, I also went and got some data off of the internet for this NGS core station. These are continually operating reference stations that you can go and get data for yourself to use and post-process from. And that's what I did and held it fixed. And the first thing you get, these are kind of switched out of order. The first thing you end up with are the adjusted latitudes and longitudes, the geodetic coordinates, and the ellipsoid height. And I held that station fixed, the core station. And then those get projected to state plane coordinates. That's what I did here in US survey feet. All right. And the next thing I'm reporting is the tabulation of my observed zenith angles being compared to what you would compute using this formula, from both ends of the lines of using the latitudes and longitudes. Whether you get those values from Google Earth, you could. You'd probably get very similar results. It's on a sphere, and so it's just it's a rough approximation, really, close enough and good enough for what we're discussing here, whether or not there's so-called missing curvature. And the zenith angles, when you sum these, you're looking at the difference. In other words, you're not getting 180 degrees. You're getting something over 180 degrees, which is indicating this tilt. And so I did it twice. I did it, earlier in the morning, and then I did it later in the afternoon. I have variation here. It's not a huge amount. It's basically 4 seconds. It's 11-second variation. You're going to have that. And if I did it again, I might get 1 minute and 4 seconds. Who knows? You're going to have variation in measurement. And that's why we use statistics to compute the precision of the result. And as many times as you repeat a measurement, you will have variation at the last decimal place or at the last significant digit. It's going to happen. That's pretty standard in any science. So I'm reporting that, and then this is the computation. You can see that, I'm within reason here. We have very good comparison here. And then I show you the miles and the curve drop using that 8 inches times the mile squared formula. But I'm also showing you a column of trig computed values using my zenith angles. And we are within reason. We're within the magnitude of a foot, let's say. If we want to round this off to a foot, then we have good agreement, and that would be reasonable for this conversation. And when we're talking about 7,000 feet, basically we're looking at about a foot. You can round it off. And that's what we're doing here. This is not high precision construction layout. You wouldn't like try to lay out a curb or a pipe 7,000 feet away. That's just not done. So let's be real about what I'm showing you here. And when you look at my other tests that I've done, looking at buildings that are 20 miles away, 30 miles away, etc., now you're talking about many, many hundreds of feet. And these videos, these flat earth videos that are talking about that these buildings and land features should be hidden by many hundreds of feet or thousands of feet, we find that that's just not the case. You set the telescope to be perpendicular to your direction of vertical where you are, and you can see many hundreds of feet of drop. It's clearly visible in the photographs. And that's really the intention behind all of these videos that I'm producing lately. And that should be understandable to anybody that's, really sincerely looking at this and trying to understand this. So anyway, I'll sign off here. If you have questions, just reach out to me. As you know, I have my comments are turned off. And, I've really stated the reason for that is that I'm not interested in any warfare over this on YouTube. Everybody can type in a description box, and everybody can cop an attitude when they're not sitting right across from you. So you get a lot of nastiness, and I'm not interested, really. So if you want to talk about this, send me an email, send me a message through YouTube, and I'll be happy to talk to you there. That's, like I said, I want to make real connections with real people that are interested in looking at this information. So I hope this is helpful to you, and I encourage you to share it with others that you think are also interested. And with that, I'll sign off. Thanks a lot, and talk to you again soon. More videos are on the way. Thanks. Bye.